Okay, so for skill 6, we're going to be doing our curve sketch steps, and now we're going to be curve sketching rational functions specifically. So with rational functions involved, we're going to have to remember our vertical and horizontal asymptote rules from advanced functions. Okay, so with a vertical asymptote, they happen at any x where the bottom is 0 and the top is not. Remember, if it's 0 over 0, then they can in fact cancel out, and then you might just have a hole in the graph, just a point missing instead of a vertical asymptote, so you should make sure that the bottom's 0 and the top is not. And that's basically all we need to know. We just need to know where they are, and then the calculus is going to take care of how they look. So there we have that. Horizontal asymptotes, you remember they have to do with I can't think right now. Sorry. The powers of the numerator and the denominator, the degree of the numerator and the denominator. So if the degree of the numerator is bigger than the degree of the denominator, then there's no horizontal asymptote. The other way, if the degree of the denominator, if I'm going to switch the words, I don't switch the sign. So if the bottom has the bigger degree, that's where we get the horizontal asymptote at y equals 0. So the x-axis would be the horizontal asymptote in that case. And then the last, so if the denominator and numerator have the same degree, then it's the ratio of leading coefficients. So there is one, and it happens at the ratio of the leading coefficients. I don't know. That looks more right. I just want to take briefly talk about why that is. So if it's some number over 0, what happens is as the bottom gets close to that x value, so let's say this is happening at x equals 4 or whatever, so something like that. As x gets close to 4, the bottom gets close to 0, but it's not 0. So you'd get something that looks like 4 over 0.01, and then 4 over 0.001. And as you get closer and closer to 0, this division gets larger and larger and larger because you're dividing by smaller and smaller things, and so the numbers get really, really big, and that's why we see the graph heading off to infinity. And then at 4, there's no point there because you can't plug in 4 to that function. So that's why the point's missing there. So something like this, degree of numerator, I want to do the no horizontal asymptote version first. So something like that, x squared over x minus 4. This one would not have a horizontal asymptote. It would have an oblique asymptote. We won't worry about that so much. I think I'll do one example with an oblique, but just so that we remember that they exist. Obliques happen when the top is 1 bigger than the bottom. And I'll often tell you just to ignore the oblique and just worry about horizontal and vertical anyway. So this happens. So horizontal asymptotes are an end behavior of the function. They happen when x is really, really, really big or really, really, really negative. So for instance, this one doesn't have a horizontal asymptote. It doesn't get close to any particular value when x is really big, because when x is really big, let's say x is 1,000,000, the top would be 1,000,000 squared. So think about 1,000,000 squared. It would have 1 with 12 zeros after it. The bottom is just a million minus 4, so the bottom is basically just a million. So that minus 4, when we're talking about really, really big values, that minus 4 doesn't really matter. So we have this ginormous a million squared divided by this relatively small, just a plain old million, and we see that we're not going to get an answer. The x squared kind of wins in that case when x is really, really big. And so nothing's happening. If I flip those around, same sort of idea. We get something that's basically a million when I plug in a million for x over a million squared. And here the bottom is just so much larger than a million. It's a million times a million. It's a million times bigger than the top. So the top, even though it is a million, it's basically nothing. And that's why this function would approach 0, because the top's basically nothing compared to the bottom. We're dividing a small number by a giant number, and we're getting basically nothing left over. When they match, so again, when we're talking about x being a million, this minus 4 and this plus 10, not really going to throw things off. When we talk about the top being a million, again, a million squared is so much bigger than just a plain old million that these just plus x's just don't really move the dial too much when we add them onto a million squared. So really the only thing when we're talking about really, really large numbers is just those these leading terms. And since they're equal degree, they kind of cancel out, and we're left with the graph getting close to 5/7 for y. So that's what I mean by the ratio of the leading coefficients. All that said, what I'll always see is somebody will do the work, and they'll have like a point here and a point here, and they'll be like, duh, and they'll be like, Mr. Clement, like I can't finish the graph. I've got to connect this dot to that dot, but my horizontal asymptote's in the middle. And what you need to remember, it's an end behavior. This logic only works when we're talking about really, really big x's, so off to the left and the right side of our page. So you're allowed to cross over that asymptote as many times as you want. You just have to settle down to it in the end. So that's the idea. So don't be afraid to cross a horizontal asymptote. So steps for graphing, we're going to do the same steps we had before. So we're going to get our x and y intercepts. Our new step, though, is get the asymptotes. So horizontal and vertical asymptotes. And then we'll do our first derivative, make a factor table. It's going to tell us increasing, decreasing. It's going to tell us our local max mins. Then we'll get the second derivative, again, factor table. It's going to tell us concave up and down. And that's going to tell us if we have any points of inflection. And then we'll do a combo table of both those things together so that we can see what shape that we're drawing this graph. So 4 of the 5 steps exactly the same. Now we just got to remember to look for asymptotes. Okay, so what we're going to do here is a beautiful sketch of this graph here to start out. You're certainly welcome to, again, pause the video, and I'll make separate videos for number 2 and 3 just so the video is not 9 hours long. So you're welcome to pause the video and work through those steps and then just check in with my video and see if you're doing the same sort of things that I'm doing. When I'm making up questions, I'm basically plugging in, messing around with functions until in software that tells me the derivative and first derivative. So until I see that they've got a nice first and second derivative. And this first one does, but because I was having the software do all the math, I didn't really notice that the second derivative is a lot more simplifying to get to that really nice final answer. So it does simplify beautifully. There's quite a bit of work to get to it. So that was not intended. And again, degree of the top is 1 bigger than the bottom on this one, so it technically has an oblique. We're just going to ignore that. I'll actually go through the oblique in the third one because it has one. So just copy it over here so that I have x minus 3 squared. All right, so x-intercepts come from when y is 0, which means the top is 0, so we get -2. Y-intercept comes from when x is 0, so when x is 0, you get 2 cubed over -3 squared, and you get 8 over 9, I believe. So that's going to be our y-intercept, so close to 1 anyway. So there's our x and y intercepts. For asymptotes, we see that we have a vertical asymptote at x equals 3. That makes the bottom 0 and the top not 0. And we have no horizontal asymptote because the numerator here is winning. The numerator has a larger degree than the denominator. So there we go. So now we're going to move on and we're going to find the derivative of this function. And so we're going to need to do this. X plus 2 cubed. So f prime is going to be 3, x plus 2 squared times the derivative of the inside, which is 1. G is x minus 3 squared. The 2 is going to come down. The 2 is going to become a 1, multiplied by the derivative of what's inside, which is just 1. And we can go along singing our song. F prime G. Minus G primed times F. Staff newsletter just came in. Gotta pause my recording and get right on that. Okay, and then over G squared is going to be that to the power of 4. Okay, and we're going to want to do something with this derivative, so we're going to want to factor it out. So again, looking for those common factors. So both terms have at least 2 of those on top. Both terms have an x minus 3 on top. We're going to be able to cancel that with the x minus 3 to the 4 on the bottom, so that'll be nice. We're going to have 3 times x minus 3, it looks like, minus 2. X plus 2 is left over, something like that. The top's going to simplify to 3x minus 2x is just x, -9 minus 4, -13 over x minus 3 cubed. And there we have it. So our key numbers are -2, 3, and 13 on this graph for the first derivative. X plus 2 squared, so since that's to a power of 2, I know that's not going to change signs. X minus 13 is negative before 13 and positive after. X minus 3 cubed is negative before 3, positive after. So we are positive, still positive, negative, and then positive. So at -2, well, we have a horizontal tangent. I believe that's our x-intercept that we already found. Yeah, -2 is our x-intercept. So we'll just remember to flatten out there, but it's not a max, it's not a min. So probably one of those squiggle roots that you would have called it, or cubic type roots you would have called it. X minus 3 goes from positive, sorry, x equals 3 goes from positive to negative, so you're going to be tempted to write max, but you're going to remember that's not a max. That's your vertical asymptote. And then x equals 13 is a minimum. And so we're going to want the y value for that, which seems like it's going to be fun to do without a calculator. So it's going to be 15 cubed over 10 squared. Ooh, that's a big number. So 10 squared is 100. Get out my phone. 225 times 15. 3375. And then move the decimal 2 spots. 33.75. And we'll keep in mind that is also a horizontal tangent because it makes the derivative 0. So horizontal tangent minimum there. And now we'll move on to the second derivative. So with the second derivative, again, I promise it is nice at the end of the day. Your two choices are either sort of expand the top out and get just a cubic, and then your quotient rule is easier to do, or do a quotient rule, but when you're doing the numerator, you need to do the product rule. So I'm really good at common factoring, so I'm going to keep it as a product rule on top. If you're not as comfortable common factoring, I would expand that out first and see what you can do with it afterwards, because I do promise it does work out nicely. So when I redo my product rule, so just for the numerator, I need to do an f prime g, a g prime f. So f primed is going to be that. G is that, plus g primed, which is 1, times f, which is that. My g is x minus 3 to the power of 3. So g primed is going to be 3x minus 3 squared times 1 for the derivative of the inside. Same formula as before, just a lot worse. So f primed to x minus x plus 2, x minus 13, plus x plus 2 squared, f primed, put that in brackets, there's a plus in there, x minus 3 cubed is g, minus g primed, oh geez, I'm going to run out of room, 3 x minus 3 squared times f, x plus 2 squared, x minus 13. Did I get all that in there? G primed f, I think I did kind of squeeze it in, all over g squared, so that's going to be x minus 3 now to the power of 6. Okay, so first things first is I'm going to factor out the x minus 3 squareds. And that's going to cancel out 2 of those and leave me with 4 on the bottom. And then I'm left with, so that gets rid of 2, x plus 2, x minus 13, plus x plus 2 squared. So that, same bracket as before, but now there's just one of those multiplied by that, minus 3 x plus 2 squareds. So the x minus 3 squared is up front, and then an x minus 13, something like that. Now, be not afraid. So if you think about this as 2 separate terms, so it's kind of like x minus 3 times that and x minus 3 times that, and then there's this third term over here, you'll see that all of those 3 terms have an x plus 2, so we can factor out an x plus 2. We're going to have 2 x minus 13 plus x plus 2 now to the power of 1, factored out of there. I've got that stuff still times an x minus 3. And I've got minus 3, x plus 2, x minus 13. And that's now all over x minus 3 to the power of 4. Trust me, we're almost there. So x plus 2 stays factored out. X minus 3 to the power of 4. And we're actually going to expand the inside now. So picture this coming over there. So you're going to get 2x squareds. You're going to get negative 13 times that, and negative 16, and then times 2, negative 32x. You're going to get 3 times 13, negative 3 times negative 13 is 39, and times that by 2, 78, I think. So that's that term. So that's the x minus 3 times 2 x minus 13s. Now we're going to do just plain old x plus 2 times x minus 3, so that's going to be x squared minus x, and then minus 6. And then this last term, so that, and then multiply by negative 3. So you're going to get negative 3x squared, and that's that. We're going to get negative 13 plus 2, so negative 11, and then times another negative 3 is plus 33x. And then the last term is going to be minus 26 times 3, negative 3, so what is that? 78, minus 78. So that's a bunch of expanding there. And I said this does work out, and I think we start to see that happen here. So we get 2x squared, 1x squared, and then minus 3x squared, so those do go away. We have, this is ridiculous, negative 32, negative 33, and then a positive 33, so the x's in fact all go away. No, this isn't working out the way I thought it would. Oh, no, not everything goes away. Good. We're left with that minus 6. That's good. So negative 6 times x plus 2, x minus 3 to the power of 4. Okay, so I'm going to jump back in here. So what you just saw is a bad edit job by me, but what happened is I had a goof in here. So I had the negative and a negative there. It should have been a plus 78 at the end. And so I'm going to edit out all the part where I went through it with the mistake and got down to an answer that just didn't make sense and I wasn't able to graph. So I'll cut out that hemming and hawing that I had there, show you what the actual answer is, but I'll show you, I haven't erased my work below this, just show you how I caught the mistake as I went. So that should be a plus 78, which makes that number in the bracket, instead of just the minus 6, it works out to 150, 78, 78, and negative 6. So when it was a negative 6 before, all of my second derivatives were the wrong way, so this should be 150, which is always positive. And that's going to flip all of these the other way. So it is now negative, positive, positive, concave up, sorry, concave down to start, and then up and up. And I've already filled this in, but here 3 is our vertical asymptote. We'll just keep that in mind. Your vertical asymptote will appear in every table every single time, so that's just something you have to keep in mind. Always looking for those vertical asymptotes. And then at negative 2, it switches concavity, it switches from down to up. We've already got that y value, but now we know that that x-intercept is in fact a point of inflection. Yeah, so here is where, with all these the wrong way, when I started to draw my shapes, this definitely didn't look like a min with those two shapes, a horizontal tangent min. So I knew I had some sign off somewhere, so I had to go find it. So this actually looks like this way, I believe. Yeah, switches at negative 2. So we have our horizontal tangent, point of inflection at -2, a vertical asymptote at 3, and a horizontal tangent minimum at that point there that we've already found. I'll draw my shapes now. So increasing concave down to start is going to look like that. So increasing and a frown, and then we're going to switch to increasing and a smile. We can see that sort of point of inflection being formed just in our rough sketch here. After the vertical asymptote, we're going to be decreasing smile, decreasing concave up, and then we're going to switch to increasing concave up like that. So I'll put those together in a beautiful drawing. So we've got, I'm not going to be able to draw that fully to scale like that. We'll just do it like this. So -2, a bit further along, there's 3, and way over here somewhere is going to be 13. Those are our things. We're at the origin there. I think that was our only intercept. Oh no, the y-intercept was just below 1, 8/9. So we'll call that 8/9. There we go. And then way out at 13, this is going to be way off. We'll call that way up there. There's my 33.75. And there's my asymptote. We didn't have a horizontal asymptote, so I think that's all of our information. So we're going to have this shape and flatten out at that x-intercept, horizontal tangent. We're going to switch to this shape, go through our y-intercept, come out of that flat, and all the way up. Then we're going to come off the vertical asymptote with the other shape there. So come down like this, flatten out there, and like that. So something like that, I guess. Something like that anyway. Should work. Super happy with that shape. Something like that is probably better, because there's supposed to be an oblique asymptote, so maybe it's over there somewhere, and this should actually be over there, but we didn't bother finding the oblique asymptote, so let's not worry about drawing it on. But that's kind of good for that kind of shape there. So we'll call this one done. I'm going to put the next example just in a separate video, so you can skip over to the next video and look at the next example now.